here to moderate the very first session of CEI seminar series. So today, I think our theme is on artificial intelligence in the context of cardiac electrophysiology. I want to thank everyone for attending the session. It's great to see a good turnout. And also thanks to Jake, Job, and Martel for organizing this year's and for bringing us two very excellent speakers. So we will have, I think we'll divide this 1 hour into 2 half-hour blocks for each speaker. We have Rutger van der Loo from University Medical Center Utrecht. I think Rutger can go first for the first half an hour. And then we also have Maxime Simonsen from INRIA ITU Lyric, and Maxime can speak after Rutger. So without further ado, I think let's welcome Rutger to start his talk on explainable AI for ECG.
Great, thank you for the introduction. I'll share my screen quickly. Cool. Can everyone see it? Yes, yep. I see the good faces. Okay, cool. So I'm Rutger. I'm a PhD student at the University in Utrecht, just like Machtel, who's also here. And my PhD is about AI and implementation of AI algorithms for automated ECG analysis. And I studied medicine and also did deep learning and AI courses, so doing a bit of both. And looking at implementation now, and one of the steps in the implementation phases of AI for the ECG is the explainability part. So I wanted to tell something about that and show some of the studies we've been conducting recently in this field. So I'm not sure how well aware everyone is about what deep neural networks are. So I'll do a very short introduction, but they're machine learning algorithms. They were first mostly used in image and speech recognition, but then it was shown that they also worked very well on ECGs. They're based a little bit on the structure and function of the human brain. They also have neurons that have connections that we use to train things. And usually we need quite large data sets for training. And one of the data sets that we've all been constructing are those. So every time you click on the images in a CAPTCHA, you're training Google's AI to learn what is shown on these images. So a little bit the difference between current computerized algorithms for the ECG and deep learning is that most currently used algorithms, they have some kind of feature extraction step. So they extract some kind of feature from the ECG signal, such as a PR interval, a P wave height, an R wave height, all different types of things. You can think of thousands of different features, of course. We enter those features into some sort of classifier, and then using the combination of the two, we perform diagnosis of interpretation of the ECG. And the advantage of using deep learning is that we combine those two steps. So what happens with the deep learning algorithm is that we enter the raw ECG. So we just enter the voltage values, a matrix of 8 times 5,000 values, something like that. We enter that into the network and we give it a task. So we say you have to diagnose atrial fibrillation, and we give it a lot of labels that have atrial fibrillation or something else. And then it learns by itself what kind of patterns or features it needs to pick up in the signal to do that kind of diagnosis or interpretation. As I think most of you know, is that since we started this and a lot of groups around the world have been looking into this type of research. This is just a few papers that I found interesting, but I think in the past 2 years, hundreds and hundreds of AI algorithms for ECG analysis have been published in all different types of journals, which ranges from things that we knew we could see in the ECG to novel things such as detecting mechanical problems with the heart as reduced ejection fraction or things like that, or looking at things that will happen in the future, or detecting specific genetic disorders, all different types of abnormalities. And I think one of the next steps now is, because I think we do know that we can make accurate models using deep neural networks. We can make very accurate models to do all different types of interpretation. But the next step is, how are we going to implement those in clinical practice? So we have recognized a few hurdles that I think we need to tackle. So one of the things, of course, that we need better studies. So there have been some trials, but not a lot. I think one on the ejection fraction, but not many. So we need better trials to see if there's really an advantage over the currently used clinical workflow before we really know that these algorithms add something. We need to look better into the uncertainty of these models so that they can express when they don't know if they can make a prediction or not, or when they're unsure about their prediction. And then there's the problem of the black box nature of deep neural networks that everyone talks about. So the thing is, because we just enter the raw ECG signal and we make some kind of prediction, but we don't really know what's happening inside. So we cannot really see what the network is doing with the data, what kind of features it learns, what it uses these features for. And it's complicated for a few reasons, I think. So it makes it kind of hard to trust what's going on here, but it's also very hard to detect biases. So it's much harder to detect that the network is focusing on things that do make sense only in this data set, or are not nicely generalizable, or that looks at the wrong features that just works here. Because we don't know what the features are, it's also quite complicated to detect biases that are in this model. And what's also a shame is that we cannot use it to learn novel features, which could be very nice, because we know that it learns features from the ECG by itself. So it would be nice if we can use that part of neural networks to improve on our knowledge of the ECG. So I want to focus a little bit on this last step in this presentation. The first approach we've been taking, and also other groups, is to look into saliency maps. So what saliency maps do, saliency or attention maps, is that we use some kind of other algorithm that tries to see what parts of the ECG were important to make a prediction. So this is from a triage algorithm that we've developed that classifies all ECGs from normal to acute. So it looks at how quickly you need to consult a cardiologist. And here you see what this network predicted this ECG as being acute. And this is due to the fact that this is an inferior myocardial infarction, where you have very typical ST elevation in the inferior leads. And you see that also the network focused nicely on that. But we can also visualize things that are not there. So this was also classified as acute, as it's a third-degree AV block or a junctional escape rhythm, where you see that there's no P wave present. And you also see that the network is focusing on this segment where there's nothing, but should be something. So we knew these things, and then we thought, can we use, these are features we all know, of course, can we use this approach to learn novel features? So that's why we got the technique from the previous paper and applied it to a novel disease group, and these are PLN mutation carriers. This is a genetic mutation that gives rise to dilated or arrhythmogenic cardiomyopathy. It's very prevalent in the Netherlands, but not elsewhere in the world. And what we did there is that we extracted the median beat ECG of these patients. So we aligned all the QRS complexes and made a median beat. And then you see some of the features visible here already. So typical features of these patients are microvoltage or reduced QRS voltage in all leads, and negative T waves in the lateral leads, so especially V6, V5, V6, things like that. And then we developed a neural network to predict if it was a PLN mutation carrier or an age and sex match control. And then we used the visualization algorithm you saw in the slide before, but now took the average of that visualization for all subjects. So instead of just looking at one of them, we thought if we average this over all subjects, we can get some feeling about what the network is focusing on. And then what you see is quite nice, is that the network uses some of the features we knew already. So it uses the R wave height in most leads as a feature. It looks also at this negative T in some of the patients that have it, I think. But two novel features were that it was actually mostly interested in the more right precordial lead, so V2, V3. There it was more focused on the T wave and also on the R wave. You also see it in the red and blue lines that you have a decreased R and T wave height there. And that seems to be an earlier feature than the negative T wave laterally, because it's prevalent in more of these patients. And we also saw it focused on the PR segment in AVR, which we think is an increased PR duration that just turns up in this lead, but could turn up in every lead, but could also be something else. And that's exactly the problem of these type of algorithms. So it's nice, you can get some kind of feeling what's going on, because you know that, so this very red means that in almost all of the subjects, the network focused on this segment. And it's like half of the subjects it focused on the R wave. So we know that, but we don't really know what's going on there. So we don't know if this is the shape of the QRS complex, or if it's fractionation, or if it's, I don't know. And also here, it could also be that it's like a PTA segment depression, or that it's the shape of the PR interval, or it's the PR duration. We're not really sure. And the same goes for all of these features. So it's nice, it gives you some feeling, and it can guide you into a direction that you can further investigate, but it's still complicated. And that's also been shown outside of the ECG field, is that saliency does not explain anything except where the network is looking. So in this image, you see, this is just an example, but you see that this is the evidence for this animal being a Siberian husky, and this is the evidence for this animal being a flute. And the thing is, both things look at the head of the animal, and it just makes a decision based on that. But we don't know what the features are there and why it thinks this is a transverse flute with a probably smaller probability, but still think it is. So that's one of the biggest problems of saliency maps. So then our next step was, can we make something better? So can we make a better explainability technique for ECGs? And that's why we started looking into variational autoencoders, and I'll try to explain that a bit to make it a little bit nicely understandable. So what we've done is we took the normal approach. So the normal approach is you have a 12-lead ECG, you put it into your neural network, and you do diagnosis, or you predict things, and then you can do both diagnosis of things we do know already, so rhythm disorders, things like that, or you look at novel things, so such as, for example, prediction of reduced ejection fraction, which is something we cannot do from the ECG ourselves, or as doctors we don't really know how to see that, but we know we can do it with neural networks. And then we've added some extra parts, because what we've done is, this is called an autoencoder, is we've taken this encoder and then made a inverse encoder, so a decoder. And then we got the ECG back again. So what happens here is we made an extra step where we put all the ECGs into the encoder that encodes it into some continuous factors of variation. So this is just 32 numbers that vary between -5 or +5, something like that. And then we use those 32 numbers again to make a full ECG. So it's a bit like compression. You just compress the signal into less variables, and then you can reconstruct the signal again from those 32 variables. And then we train this first network, this upper part. We train it using only the ECGs. So there's no supervision, there are no labels. We just enter 1 million ECGs or so. I think we have 1.2 million. We just enter all of those ECGs, and we make the network learn how to reconstruct the ECGs. And then we also force it that these 32 factors are independent of each other, so that they all try to learn a different factor of variation that makes up an ECG. And then in the next step, we can use those 32 factors in different models, such as logistic regression or Cox regression or anything, to do the tasks we wanted to do. And the nice thing about this is that we now know what the network is using for its predictions, because we can look at individual ECGs and we can see the state of the factors. So for example, here, a normal ECG, most of these factor values are around 0. So if you enter a normal median beat ECG and you get the reconstructed median beat ECG, and all these values are around 0. But if you enter a left bundle branch block ECG, you see that the factors look completely different. And for example, what we see here is that there's a very low value in factor 26 and a higher value in factor 9, for example. And when you look at those a lot, you know that this combination is a left bundle branch block. This is a T-wave orientation, and this is your QRS duration in combination with the shape of LBTB. But also, for example, rhythm disorders are also encoded into this factor ECG. So for example, a sinus tachycardia, you see a higher value for factor 10, while all other values are still around 0. So they are still, because it's mostly a normal ECG, but only this factor is different. And because we know we use an interpretable model here, we can see at the individual ECG level what happens. So for example, if this ECG was classified as an LBTB, and we know that the weight in your interpretable model for factor 26 was very high, we know that the combination of this was very low, and the combination of this value plus that weight makes sense. So this led to this decision. But we can also look at the model level. So not only at the individual ECG, but at the complete model. And how that works is we take those 32 factors, we put them all at 0. So then you get a mean ECG, which is a normal ECG in this case. And then we start varying all these individual factors one by one. So we keep all 32 0, and then just, for example, here, factor 26, we vary its value from -5 to +5. And then we can, using the decoder, we can plot all the ECGs that are made using these values. And then you can see clearly what we saw before is that this factor has learned to make the morphology of a left bundle branch block. So if you make its value lower and lower and lower, you see a morphology plotted that's more like a left bundle branch block. The same goes for factor 10. That's the ventricular frequency. So what happens is that when you increase its value, the ECG changes according to the frequency with a shorter QT interval, and you see the T wave of the previous complex coming into the screen. And when you decrease its value, you see a lower ventricular frequency with a longer QT interval. So we now know on a group level, so on the complete population, what every factor, what for ECG morphology every factor has learned. And then when we look at the performance of these models, we see that if we use this approach, so where we take the ECG, make a factor ECG, and then put that into our interpretable, easy logistic regression model, we see that the performance is just as good as using the black box model where we don't know what's going on. So that's actually quite nice, because now we can use the power of the neural network that makes predictions with very high accuracy, but also have a feeling what kind of ECG morphology was used for every classification. And one thing that's, for example, interesting is this prediction of reduced ejection fraction, because that's something that we cannot do by the ECG visually. We don't really know what the features are of a reduced ejection fraction. But when we use the explainable DNN, we get the same performance as the black box. So this is just overlapping confidence intervals. But now we also know which features were important. So, example, factor 5, which is a T-wave shape and orientation feature, and factor 10, which is the frequency feature. But also an interesting feature is 1, which represents ST elevation and depression. And this is a very problematic one, of course, because what happens here is that we train this network on a hospital population where there are a lot of patients with acute ischemia and also reduced ejection fraction due to the acute ischemia. And this is also one of the features the network picks up. And this is one of the biases you can learn using this approach, because now we know when we apply this algorithm in a general population or at home or other settings where you want to apply it, then we know that there are no patients with acute ischemia there. So it might not work as well. So we might need to exclude some patients from our data set or things like that. So I think that's the added value of using these things. But another added value is that we have performed an enormous dimensionality reduction. So we have reduced this network that has millions of parameters to only 21 variables. So we choose 32, but there are only 21 that are really important and really encode different things. And that made novel applications in smaller data sets possible, because now we don't need this enormous data set with 1.2 million ECGs, but we can just use data sets with hundreds or thousands ECGs in very specific patients that have specific abnormalities, and use the network there to do other tasks that we want to use in practice. So it is a full list of things, but we've tried all different types of smaller diseases. We tried to factor ECG to learn novel things. So for example, in DCM patients, we use this algorithm, and we can get AUCs around 0.7 to predict ventricular arrhythmias in these patients, something that wasn't really possible because we didn't know any features from the ECG. But it turns out it focuses mostly on P-wave abnormality. So for this prediction algorithm, the most important features was factor 8. As you can see here, this factor learned the PR interval and the P-wave shape. So the higher the value, the broader the P-wave, the longer the PR interval. But also factor 15 and factor 27 are all focused on P-wave. And this is also axis, but also P-wave abnormalities. Which is quite interesting because we didn't really know that. And now using this approach, we have much more feeling about what's going on while still having a fully automated pipeline that can interpret ECG by itself. So here's an example. Here you see one of the patients that had a very short PR interval. Then you get a very low value for factor 8 and a low predicted risk of life-threatening ventricular arrhythmia. And here's another patient that has a very long PR interval with a very broad P wave. You see an exceptionally high value for factor 8 and also a high predicted risk. And this patient also got his ventricular arrhythmia quite early. Now we also use this in CRT patients, but I think there's no time to show all of that. And also in the PLN patients where we used the previous approach before, but now also this novel approach, and we see that it works much better and we get a better feeling. For example, that this factor 5, that produces T-wave, that has a T-wave orientation, that's a very important factor in predicting ventricular arrhythmia in these patients. And we're now looking at this is just first results at these factors and if we can relate them to genetics in the UK Biobank. So that's a work in progress, but also something that is coming soon. Some things that need to be improved are especially that it's not perfect yet. So the reconstructions are not 100% the same as the ECG that we use as input. So we're looking into that if we can improve that. And we are looking into new ways to make this more explainable to clinicians because it still needs a lot of explanation, like to understand the concept of this. And that's also something we want to improve. And there's an online tool where you can visualize what's going on. So you can change all these different factors and you can see the ECG changing, which is quite nice, but I don't think we have much time for that now. Thank you, and hope there are questions or let me know if you want to know.
Thanks very much, Rutgers. Really great talk. Do we have questions from the audience?
Yeah, so thanks, Rutger. This is really cool, especially, I want to ignore my first question because the second one's more interesting to me. So I really like the idea of using the VAEs to, come down to a compressed feature set. And it seems like the features, the output ECGs that you were getting, there was sometimes one aspect that changing that knob would change about the ECG, but then other times it seems like it was having kind of a complex effect, like it changed the P wave over here, but QRS over here and stuff like that. So I'm wondering, do you think that this will eventually translate into more like clinical intuition, like give a doctor an idea of what they should be looking for? Or is it more just a tool to say, hey, be more confident because this thing is looking at, reasonable parts of the signal?
Yeah, so I think there are two things. I think the first part, what we can do right now is, of course, have a better feeling about what the algorithm is doing and then know when it's biased or when it's using the wrong features. And what we really hope is that we can also use it for the doctor to have him know new features. So for example, these T waves, you can say like this for this disease, you need to look at negative T waves in these leads, for example. And that's something that you can also do, of course, by using these ECGs manually and just ticking these boxes all of the time. But now it's something we can do automatically. But I agree with you. What's still problematic is that some of these features, they're not. So a lot of things in the ECG are very related, of course. So there's like something happening at the T wave and the P wave at the same time, or these things are related, or it's like the orientation of your heart that changes multiple things at the same time. And this network is we just give it the data and we don't force it to learn anything, learn specific things. So that's still complicated, and we're looking into if we can make it still more disentangled, as it's called, and that we have really specific features for every factor. But that's a still complicated part. Yes.
Thank you.
I have a quick question. So it's really interesting to see the sort of the meaning you discover in the latent space for the ECG. So one of the things my group also does a little bit about the VAE in learning different data. So one of the challenges we always discover is trying to actually find those meanings, because we have to, my students have to stare at the data and try to, like what you were saying, try to change the value in the latent space and then see how the data change in order to understand what is changing. And then every time, when you change your latent dimensions, then all those meanings sort of changes again. So I was wondering if you can comment a little bit on that. Like, how did you go through the process of discovering those really, really nice meanings of all those different latent factors? And how did you come down? What was like a dimension of 36 or dimension of 21, something that you arrive at after a lot of sort of experimentation? Or
exactly. Nice question. I think it's a hard process to train a good VAE. It's not really easy. So I think we just did an enormous hyperparameter search. So we investigated all different types of latent space sizes, architectures, but especially also, so this is a beta VAE. So there's another parameter that can control how disentangled the latent space is. And that was especially an important one. So what we saw is that we could increase and decrease that. And when it was too low, you got all these features there's too much correlation between the features, so they're very hard to interpret. And when you put it too high, it turns it back to only 5 features or so, but then the reconstructions get really bad. So in the end, it's like a trade-off, right? So you find a network that has the best reconstruction while still providing you features that are visually interesting and visually understandable for us as doctors. I think that's where we ended up, and that was around 21 was the number where we ended up in the middle with good reconstructions and still features that we could understand. So that's a bit how we got here. Yeah.
Great, thanks. Yeah, I think what you discover in the end is really interesting, but there must be a lot of work, I can imagine. Do we have any new questions?
Yeah, we do have a question from Joop. So.
Yes, I would have one. Thank you very much for your very interesting talk. I think we can definitely learn a lot from these explainable AI methods. I am mostly interested in your view as a clinician, because you're also an MD, right?
Yeah.
So how far do you think we are away from clinical implementation of these methods? Is it mostly the understandability that's the problem, or is it mostly the sheer amount of data and or the multi-class classification that you would need to do if you want to really implement this in clinics?
So I think not that explainability is not even the biggest hurdle here. I think it's super interesting, especially during the development phase, because you can look at biases, you can learn novel features and things like that. I think the most important steps now before we can implement this in practice is first that the software is not made for it. So it's there's no software package or software platform or something like that where you can easily deploy such an algorithm in practice. You know, of course, it's a lot of work and there's a lot of MDR and software development needed, I think, in that part. One other thing is I think that we really need to look into this uncertainty part. So if we can really express how uncertain the network is and then exclude some ECGs that we don't want the network to look at, because we know it's not certain enough, and have these been interpreted by a cardiologist, and then only the other ones we can do automatically, that would help a lot. And I think the final step would be that we just need real implementation studies. So we need this software platform that we can test these algorithms in practice, and then we just need to look at real patient outcomes. So if we implement this algorithm to look at reduced ejection fraction, does it improve outcomes? Do we detect patients with heart failure earlier? And does it make it better on the long term? Because that's always the problem with these things. They are very much also all our things are very much data driven. So we have a big data set with echoes and ECGs combined, and everything. Oh, it would be nice to look at reduced ejection fraction. And you just do it and you see that it works, but we really don't know if it also really improves patient outcomes, I think. So that's one of the things we have to show. And I think the biggest hurdle is just technical, that we just need a platform to do this. But yeah.
Now we have to move forward to the next speaker, Maxime from INRIA, who will talk to us about machine learning in terms of for the purpose of improving cardiac modeling.
Thanks. Hi, everyone. So yeah, the idea, I mean, as you know, when you are at this interface and looking at patients, I mean, from modeling, you can go from cells to the patient and try to increase the realism of your models. But if you look the other way around, AI is a bit going from a group of patients or a cohort, a population, and then trying to statistically explain or show how a patient is different from this group. So, I mean, there are now more and more activities at the interface between these two areas of biophysics and AI, and it can help both ways with AI bringing, as we saw, some statistical approach to estimate parameters or do some model reduction or uncertainty quantification. And the other way around, biophysical modeling can help bringing mechanisms and causality explanations to what has been shown statistically by AI. It also can generate data and features. But what I wanted to present today is, can we try to more directly combine these two areas and use directly deep learning to do the cardiac electrophysiology modeling? And this is something which has been also quite active these past years, because there are many similarities between the numerics involved in deep learning and solving partial differential equations. And I mean, there are some architectures which are similar to time integration schemes like a residual neural network. And if you look at spatial derivatives, they are equivalent to convolutions on a Cartesian grid. So it's quite natural to try to use one tool to solve the other problem. And as you may know, I mean, once you train a neural network, then it's very fast to do predictions on new data. So potentially this could be faster than solving PDs with classical solvers. And also, if you train on a given time step, I mean, the stability of your neural network will be directly related to the data it will have seen during training, but not necessarily to the constraints given by mathematical equations. So potentially, you can train a network with much larger time steps than what you use in a standard modeling solver. So it can also be very fast. But then you lose the intrinsic physics of PDs. So how long can you forecast with this is still an important question. And even more important, I think, is what can you really gain from doing this? And to me, what is really interesting when you try to integrate neural networks in solving equations is that potentially you can go further than the original model. Otherwise, you are just making a faster solver, but you don't necessarily gain a lot. So yeah, there have been, as I said, quite a lot of activity around deep neural networks for solving differential equations, or even to learn equations from data with like symbolic regression. And one aspect is to try to directly replace, as I said, the solver of the operators by a neural network. And we've been doing that a few years ago at FIMH, but on very simple geometry and quite standard initial conditions. So the question was, if you train a network to solve an equation, how well does it generalize to different conditions and computational domains? So that's what we explored last year. So we trained a network just with one standard scar, let's say, call it a scar. I mean, a rectangular domain changes and just one pacing location. And then the question was, can the model still generalize to several pacing locations and any shape of scar area? So that's what we tested. So we used the Mitchell-Schaeffer model because it's quite easy and fast to simulate. So that's this two variable model of the transmembrane potential. And so we work on a 2D slab, square slab. So the first difficulty for neural networks is that only one of the two variables can really be observed. So if you want to exploit this, it means that the network has also to predict the hidden variables. And the idea is that we replace solving these equations by a neural network. So to do this, there are different ways to do it. What we propose is that we replace the computation of the derivative by a neural network, which we're going to predict the new value of the derivative, and then use this in a classical forward layer integration scheme. And to introduce non-conducting areas, we have a penalty constraint that imposes that there is no propagation in these areas. So we have this loss, which combines a good prediction of the propagation and a good prediction that there is no propagation in the scar area. In terms of in practice, so it's also based on convolutional neural networks with some residual blocks. And this has some similarities, as I was saying, with a standard forward layer integration. And in our case, so we provide to the network 4 time steps and the mask of the non-conducting areas, like the scar image. And then it predicts the next, the derivative for the next time step that we then integrate in a forward layer scheme. So here's an example of a propagation with you can see the mask with this square scar in the middle and the true propagation, and then the propagation which is generated by the trained neural network. And we can see quite a good fit on the dynamics and on the shape of the transmembrane potential. And what was interesting is that we could see that it was robust to any shape of scar and any number of pacing conditions, even at different numbers. So that was reassuring in the sense that the neural network really learned local dynamics. I mean, really learned how to replace Laplacian and the kind of operations we do in reaction diffusion equations. And so it can then be quite flexible and generalized to different conditions and boundary conditions. But if you look at more cases, first there are some cases which are difficult because in this convolutional neural network approach, you work multi-scale. Often so there are some scales where maybe your scar will have holes. If you take a very thin scar like the circle that we show in the middle, we can see that it's leaking with the neural network implementation. And we think it's because it's so thin that with the different subsampling steps, at some point, this is not continuous anymore. But more importantly, in time, we look at very small sample size. I mean, it's like 4 frames and we predict the next one. So it's very hard for the model to learn a larger time scale. And in transmembrane potentials, we could see that we could really predict nicely the depolarization. But the repolarization was missed because the network never really sees the whole phenomenon. So it cannot really learn this kind of slow dynamics. It can only learn the fast dynamics. So that's why, yeah, we think that it's interesting, but probably quite limited because it's still very hard to replace all the physics involved in the models. And again, at best, we can do what we saw in the data. So if the data was generated for a model, it means that at best, we're going to do like the model, so which may not be that interesting. So maybe there are better ways to combine machine learning and biophysical modeling. And actually, so what we want to propose is to use deep learning to correct models rather than replace models. So yeah, these are very recent results actually that are going to be presented in June at the Middle Conference. So it's still quite preliminary, so bear with me. But I think the concept is interesting. And so it's work with collaborators in Paris who developed this affinity framework, which is an interesting way to combine machine learning and modeling. And the basic idea is that if you have a given model, you may be, so the example at the bottom is if you have a damped oscillator in red, and you try to predict with the model, the blue line, if you are purely data-driven, then in the long term, you see that you really diverge from the real model because the dynamics are too complex to really predict with a neural network. But then if you have a physical model which is too simple, so like the not damped oscillator, you can see that you get the right oscillations, but you lose the damping. So the idea is, can we use a model which is probably too simple, but augment it with a data-driven part so that the combination of the model and the data-driven part can really represent the physical phenomenon you are observing. So that's this framework where if you see the dynamical systems at the top, then you can replace the model by the sum of a term which comes from your model and a purely data-driven term. And the idea is that there is an infinity of ways to combine a physical-based model and data-driven term to solve this problem. So the way it's framed is that we are looking for the minimal norm of the data-driven part. So we want the data-driven part to really just correct the residual error between the best model we can do and the data. So for this, it means that as we are training the model, we try also to estimate the parameters of the physics-based part so that our simplified model is the best as possible given the data. And then we add this data-driven term with the minimal norm necessary to correct for the remaining error. So here's how it works. So you've got data, and as I said, you've got two different parts. So one coming from a PDE. So in our case, it's a simple EP model, and then the data-driven term. And when you train your network, your algorithm, you simultaneously estimate the parameters of your model and the data-driven part. And then you solve for a complete dynamical system, which is this combination of a physics-based model and a learned model. So in order to test this idea, what we did is that we used data from a 10-Tusher model that some of you probably know, which is one of the more advanced model of ventricular transmembrane potential. And then we used our simple Mitchell-Schaeffer model and try to see, can we use this framework to learn the difference between the two models. So this is still quite preliminary, but it's just to show you the idea. And so what we observed is that if you look at the results, it does manage to quite reproduce well the dynamics. So the top line is the 10-Tusher model, and the middle line is the combination of the Mitchell-Schaeffer model with this data-driven part, and the bottom line is the error between both, which is quite small. And actually, if we look at what happens, so this is a dynamical representation of this. But if you look at in more details what happened, actually, so here again on the top you've got the ground truth 10-Tusher propagation, and then below it you have the simulation from the physical model, which is the one from Mitchell-Schaeffer, and at the bottom line you've got what is generated by the data-driven part, and you can see that if you look at the difference, it's mostly on the circle, so on the front, on the propagating front, that there is a need for a correction between the 10-Tusher and the Mitchell-Schaeffer model, because the rest of the potential shape is quite similar. So it seems to show that the data-driven part of our final model is really learning the difference between the two models, and that it can bring this kind of residual error correction that we were hoping it would bring. So that's what I wanted to present you today quickly, and I'll be happy to discuss this further. So the idea is that given the lot of progress of deep learning, and you can learn any type of relationship between input and output, and I think there are many publications now showing that you can replace solvers by neural networks, but it's not always clear how much this really brings, because it's often trained by on a very academic geometry and on a given set of simulations, so it's quite limited to the model it was trained on. So to go to real data, I think it's interesting to more combine learning and modeling in a way that learning adds to the existing models rather than trying to replace them. So thank you for your attention. I'll be happy to discuss this further.
Thanks very much, Maxime. Very interesting. Now we're open for discussion. Are there any questions from the audience?
There aren't any yet in the chat, but I don't know if somebody wants to speak out.
I can start with one if there's and when we're waiting for more. Maxime, I was curious about in the diagram that you were showing, there was a model parameter that was being estimated for the physics model. Was the data-driven model also will be considering different model parameters, like the scar mask you had in the first example, or the data-driven part won't be worried about the parameters?
I went a bit fast on this. One aspect here is that so we solve. You have to solve your equations within your deep learning framework, because actually, because the solver is in the same framework, it means that we can have when you have your loss function between your physics-based model and your data, then your back propagation can also change your parameters of your physics-based model, so it fits best the data. So everything is integrated in the same framework, so that when you estimate the parameters, you estimate both the parameters of your neural networks and the parameters of your PDEs, because you're solving them in the same pipeline and in the same
Right. So in this setting, the assumption is the neural network part is no longer concerned with the parameter, like those like the scar mask, like what you have in the first.
Hopefully this is all the physics-based model will take care of this. So all the kind of changes in the computational domain and changes in boundary conditions and long scale in time dynamics, which are hard to capture, this should be taken care of by the model, which is very capable of this. And then the data-driven part should be the correction from the data-driven learning.
Yeah, thank you. Looks like Rob has a question. Rob, do you want to just speak up?
Sure. Thanks, Maxime. This was very interesting, and I love this notion of bringing the two domains bringing the strengths of the two domains together. I think this really is where we have to go. So I'm curious, in that framework, how far you've been able to push the making more realistic elements in the model, anisotropic models with more realistic shape, models with regions of slowed conductivity, these sorts of things. Do you build those exclusively into the deterministic side, or how does the machine learning guide the parameters you need to set there?
Yeah, that's a good question. I mean, as I said, it's still very preliminary. So we are in a 2D setting in a square and with quite crude changes. But I think it's up to the user also to set the threshold. And for instance, I'm sure there are many aspects that Mitchell-Schaefer model cannot really represent, like maybe effect of drugs or genetic defects or these kind of things. And if you decide it's better to have maybe a simple model like this one, which is fast to simulate, and then put the residual errors in the data-driven part, that's probably an idea. And then you can see on the data-driven dynamics what was added or what was changed to your model to be able to capture the data. So, but up to now, we haven't really tested this in practice. But in the idea of the framework, that's how I see it could be used to go to this. Yeah.
Great, thank you.
I guess follow up on my earlier question. So it's very interesting the part that the the model is able to both estimate the parameter of the physics model and then also identify the rest in the neural network. So I'm curious about right now the parameter for the physics model, the theta in the diagram. What form is it? Is it like high dimensional parameter that covers the part, or?
Yeah, but I know, again, the tests we did were quite simple, where we just modify the conductivity globally. I mean, these kind of things. I mean, like few parameters that are changed and that are then estimated. So, I mean, I guess it has the pros and cons of the kind of gradient descent. So, first of all, as always, you need to parameterize your parameter maps in a good way. And probably if you try to estimate too many parameters at the same time or too locally, it can have many local minima. I mean, it's the same as personalizing a model classically. So I guess it has its same limitations. And if it's too noisy, it's still kind of gradient descent. So it can also be trapped in local minima. So, but I think it potentially you could do any kind of approach that estimates these parameters. The constraint, as I said, is that it has to be compatible with the backpropagation, with the neural network training, so that you can do both at the same time.
Right. And in terms of computation, how I imagine I guess what's the additional cost in terms of embedding a model that's running? So it's ODE that has to be solved at the same time the neural network, and that have to be updated.
I mean, on this square, I mean, on this kind of setting, simple setting, often it's not a huge issue. I mean, what I showed, I think, is trained in a few hours. But it does require during training to solve this quite a lot of time. So it can also generate some difficulties. And I mean, as usual with deep neural networks, you've got some kind of subtle balance to find between how you initialize things and the learning rate, how it changes, and the losses also, how you combine the losses. And so Victoria Castanova, the student who is working on this, and tried different ways to do it. And I think the code is on GitHub, and it's but there are also some difficulties inside to make everything work nice and smooth.
Yeah, it is very interesting. I think to me the most interesting part is that because the parameter of the model, of the physics model, explains the difference between the model output and the data, and then the neural network part also explain that difference. So it's interesting to see how these two sorts of difference can be estimated back to their own so the corresponding sources. I was trying to think if there's some constraint that might help to figure out the residuals caused by this versus that. But it's very interesting. I think it's a really interesting direction.
Yeah,
Any
so we're going to
further
have,
questions from the
hopefully this
audience?
will be an ongoing series
If
on a
not,
every
we
other month
can
or so
thank our
basis.
speaker.
We're still putting
And
together the next talk.
thanks
for
Maxime,
sometime
and
in,
thanks
May,
Rosberg
I
for
believe.
great talks.
So there'll be more
And-
information coming out about that. through
And
the same
Jake, do you
channels
want
that
to
we brought
do you
out
want to
this
say
time.
something to wrap things up and maybe introduce next session?
If anyone is interested in participating in one of these talks, feel free to reach out to any of us on the CEI exec board. And thanks everyone for coming.